Good day, everyone. This is the video that accompanies the handout you're getting in class for the review of Unit 5. This handout is called Math 30-1, The Straight Poop, Unit 5, Logarithmic and Exponential Functions and Equations. And as I've told you in class, I'm not going to spend class time going through this. I'm recording this video so that you can, a little bit later, sit down and relax and watch the video. Like I said in class, I think this is time well spent. The video will probably be about 30 minutes long. So if you're starting to watch this, once again, I think it's time well spent. I think at the end of this video, you'll feel better about where you're at in terms of what you're remembering content-wise in this unit. Once again, these reviews that I give, called The Straight Poop, are not intended to go through a whole bunch of math problems. They are intended to go through the content piece by piece in a review fashion to kind of remind you of what we've learned. So to begin with, we started off the unit by looking at what I called basic exponential functions. And by a basic exponential function, I mean f of x equals a base raised to the x. We did have some conditions on that base. The base had to be either a number between 0 and 1 or a number greater than 1. When we take a look at a graph that's a typical exponential function, y equals a base to the x, and looks like this, this is what we call an increasing exponential function. Whenever we talk in math about a graph increasing or decreasing, we're always interested in what it's doing as we go left to right on the graph. So as I go left to right on this graph, the value of y increases. If you go in the other direction towards the left, you will see the graph creeping closer and closer and closer to the x-axis. It will never reach the x-axis, and that's why the x-axis, or the line y equals 0, is a horizontal asymptote. On the other hand, you can also have exponential functions of the form y equals a base to the x that are decreasing. So as we go left to right on this graph, the value of y decreases. What distinguishes these two graphs from each other is the value of the base in the exponential function. If the base is a number bigger than 1, then the graph of the function will show an increasing trend. But if the base is a number between 0 and 1, it will show a decreasing trend. I'm not going to get into the details of it, but you should be able to recognize what happens to a graph, for example, an increasing function, as the value of c gets larger and larger. In other words, you should be able to recognize, given two graphs, which one has a bigger value of c if they're increasing. And similarly, you should be able to recognize that for decreasing functions. Both of these functions have y-intercepts of 1. And as is always the case since the beginning of the course when we learned about transformations, those parameters a, b, h, and k, which I'm not going to go through the effects of, you should know by now what a, b, h, and k do to an original function. You should be able to apply those transformations to any of those exponential functions so that you can determine properties like y-intercepts, locations of asymptotes, all of that kind of thing, including domain and range, based on transformations. Exponential growth and decay is a huge part of this unit. This is the formula that we use to analyze any exponential growth application or any exponential decay or decline application. And in this formula, there are 5 different letters: y, t, a, b, and p. But as I've said numerous times in class, I think it's crucial that you understand that there's 2 classes of these letters. They're not all variables. Y and t are variables. So in other words, if you sketch a graph of this equation, you will have y on the vertical axis and t on the horizontal axis. They are variables. Whereas a, b, and p are parameters that define a particular application. So if I have $10,000 that I deposit into an account that pays 6% interest compounded quarterly, then the value of a, b, and p for that situation defines that problem. Whereas if I deposited instead $8,000 in an account that pays 2% interest compounded semi-annually, I'm going to have different values of those three parameters. To just run through what all of these are, y, of course, is the quantity that's growing or declining. T is the elapsed time. A is always the initial quantity that you start off with. You can make a mental note here that A is always going to be the y-intercept of the function, and we'll see that in a minute. B is the factor by which y is changing regularly. So briefly, and I'm going to go through numerous examples in a minute, but briefly, if I told you that something was doubling in value regularly, then B would be 2. P is the length of time that's required for that effect to happen. So going back to my doubling scenario, if I told you the number of viruses in a lab sample was doubling every 5 hours, then you would say B is 2 because that means it's doubling, and P would be 5. As it says on your handout at the bottom of this page, on the next page I have some examples that I'll walk through with you in just a second. Clearly, exponential growth is a graph that looks like that, and exponential decay is a graph that looks like that. As some illustrations to remind you of how to find B and P, if I told you that we had a radioactive isotope that's decaying, and it has a half-life of 34 years, well, even though this isn't a Physics 30 class, Math 30 students are expected to know that this means every 34 years, 1/2 of the number of nuclei will be gone. They're not entirely gone, just to steer into a physics lane for a second. They are no longer the same type of nuclei they were. They're turned into something else. But essentially, the number of the original nuclei is going to be cut in half. And that means B has to be 0.5, and 34 years is the half-life. It's the time it takes that to happen. If I told you that a population, it could be a population of mice, a population of bacteria, a population of people, it doesn't matter. If I tell you a population is growing by 4% every year, then what happens is by the end of the year, the population is 4% more than what it was at the beginning. So if you assign a value of 100% as being the population at the beginning, and we add 4% to it, at the end of every year, you're going to have 104%. And of course, percent means divided by 100. So B is going to be 1.04. And P is 1 year because it says it happens every year. If I have a value, it could be a value of anything. It could be a value of a recently purchased vehicle, and it's declining by 12% every 6 months, then that means you start off with 100% at the beginning of, and if we lose 12% from 100%, that takes us down to 88%. 100 minus 12 is 88. And 88% means 88 over 100, which means B is 0.88. P is 0.5 years. If you want to use months, you can use months, but you just need to be aware, whatever the unit of time is you use for P, that has to be the value, or rather the unit of time you use for T in the equation. So when you start plotting points or putting in a time into the equation, if you use P equals 0.5, you have to put T in years. If you use 6, you have to put T in months. One final example, 8% interest compounded quarterly. What this means is the bank is saying, we're going to give you 8%, but we're going to divvy it up into 4 chunks, because that's what quarterly means. Which means every quarter of a year, you're going to get some interest, but you're not going to get 8%, you're going to get a quarter of that, which is 2%. And that means that every time they calculate interest, which is every 0.25 years, they're going to multiply your investment by 1.02 so that 2% is added. Once again, you can use years or months. Just to let you know, I prefer to use years. It doesn't matter, it's just a preference. So anytime you ask me to do one of these problems for you or to help you with one, I will say, let's do it in years. Now we're into logarithms, and we're going to talk here about the origin of a logarithmic function. The inverse of an exponential function is called a logarithmic function. So I'm going to use a specific example a little bit later maybe, but for the time being, I'm going to use the most general form of an exponential function. And I've switched to b here for the base instead of c. Again, it shouldn't matter. They're just letters. If I say what is the inverse of y equals b to the x, we've learned in the first unit that what you need to do is switch x and y. So this x equals b to the y is called a logarithmic function. These are inverses of each other. You should know, and I've just reviewed it 5 minutes ago, what y equals b to the x looks like. It's that bluish graph. I am using a base greater than 1. You should also know from the first unit that an inverse is a reflection across the line y equals x. Or you could start plotting individual points on the blue function, switching x and y coordinate values to get new points to plot the red function. But that red graph is the logarithmic function x equals b to the y. Now, we don't like to write x equals b to the y. We write y equals log base b of x instead. So if we go back to the beginning, here's the exponential function. This is the inverse, which is the logarithmic function, but x equals b to the y is the same as y equals log base b of x. So if you keep your eyes on that x equals b to the y that's highlighted, that's what we write instead. We could write x equals b to the y, but we don't. We would much rather, and almost always do, write y equals log base b of x. And it's the same with this label on this red graph. We probably wouldn't write x equals b to the y. We would write y equals log base b of x. That leads to something, so those are inverses of each other. That leads to something which is more global in your understanding of logarithms. Logarithms do not have to be about graphs. You need to understand that there is an exponential form of an equation and a logarithmic form of the equation. These are not inverses of each other. These are the same thing. And you need to be fluent in both languages. You need to be able to translate the exponential form of an equation to a logarithmic form of an equation. And we've done numerous examples of that. Before I go on, just a reminder here of what I've told you in class. If you're working on a problem and it doesn't make sense to you, you're confused about what it is you need to do, if it's in one of these forms, rewrite it in the other form, and very often when you rewrite it or translate it to the other form, it becomes very clear what you need to do. Logarithmic functions in general, so I'm going to talk here about the graph of f of x equals log base c of x. I'm going to remind you of this a little bit later, but the argument of a logarithm must be greater than 0. And I'm not going to go through why in this video other than to say, if you want, try to determine what the base 2 logarithm of negative 12 is, or try to determine what the base 2 logarithm of 0 is. By writing them in exponential form, you will soon discover that it's an impossible situation. So you can never take the logarithm of 0, and you can never take the logarithm of a negative. If we're graphing y equals log base c of x, and c is a number greater than 1, then this is what the logarithmic function looks like in general. It has a vertical asymptote on the y-axis. In other words, the vertical asymptote is x equals 0. It has an x-intercept at 1. And again, this is if the base is greater than 1. This is what would happen if you reflect an exponential function that has a base greater than 1. If, however, you were to reflect an exponential function that has a base between 0 and 1, in other words, if you were to reflect a decreasing exponential function, this is what the resulting graph would look like. So this is what, on the right, y equals log base c of x looks like if the base is between 0 and 1. And just like we've said for exponential functions, and we've said for radical functions, and we've said for trigonometric functions, you ought to be able to apply the transformations associated with a, b, h, and k to y equals log base c of x so that you can tell me something about the resulting function. Laws of logarithms, briefly. These are on your formula sheet, of course. The product law is not a law for the product of logarithms. It's a law for the logarithm of a product. So the logarithm of a product of m times n is equal to the sum of the individual logarithms. And this is all base b. These could all be base 2. They could all be base 10. They can be any base that's allowable. In other words, has to be a base between 0 and 1 or greater than 1. The quotient law is a law for the logarithm of a quotient. Of course, the order of operations here is sensitive. The logarithm of m divided by n is the logarithm of m minus the logarithm of n. You have to subtract them in a particular order. And then, of course, the power law says that the logarithm of a power is something like m to the n. A logarithm of a power is equal to the exponent on the power multiplied by the logarithm of the base. And we use these for a number of situations. We use them to rewrite equivalent expressions. We use them to simplify expressions sometimes. Sometimes we use them to make solving equations easier, whether they are exponential or logarithmic. The change of base formula. This is, of course, on your formula sheet. You don't need to use it. I can't really come up with a situation where you absolutely need to use this in Math 30-1. I would say to you that it's mainly for those people who have a calculator that does not have the log base function where you can evaluate logarithms of bases other than 10. You may find uses for it even if you do have that function on your calculator. It's not a big deal. It's just mainly for those people that don't. Solving exponential equations. What you can do if a common base is possible. So if you have bases on the left side of 16 and bases on the right side of 64, it turns out you can write those both in base 4. And if you can, this is the way to go. So if you can rewrite both sides of the equation with a common base, do so. Simplify it until you have a single power equals to a single power with the same base. Then you can set the exponents equal to each other and solve the resulting equation. If a common base is not possible, then at some point you're going to have to take the logarithm of both sides to move those exponents which contain x in front and then solve it. There's a lot more to this than just saying, oh, then solve. You might have to expand things. You have to move all of the terms with the x to one side and the terms without x to the other side. You're probably going to have to factor x out. There's algebra involved. But that's the math we've been practicing ever since we started high school math. The Math 30 is you take the log of both sides to move the exponents in front, then you use all of your skills to solve for x. When we're talking about logarithmic equations, it's kind of the same thing. If it's possible to get a single logarithm equal to a single logarithm, as long as the bases are the same, then you can forget about the logs and solve the resulting equation. In other words, using your laws of logarithms, you can end up with log base 8 of one thing equals log base 8 of another thing, and then those two things have to be equal. Sometimes, however, when you have a logarithmic equation, you're missing a logarithm and there's a number in its place. And what you can do then is simplify it so that you have a single logarithm equal to a non-logarithm, but then you just write it in exponential form and solve it. By the way, there are other applications and other types of equations, particularly with logarithms, that are not summarized here. We looked in class at quadratic logarithmic equations as an illustration. One of the things to remember, though, about a logarithmic equation is you have to check for extraneous solutions. If your original equation contains a logarithm, you need to remember that the argument of the logarithm must be greater than 0. So if you have in your original equation log of x minus 1, then whatever you put in for x, that you get for a solution to the equation, when you subtract 1, that thing must be positive. So the argument of a log must be positive. If it turns out that when you do that, you get a negative, well, then it's not a solution. That's one way to do it. You ought to be able to as well write the restrictions as an inequality statement. And there are many examples we did in the previous lesson dealing with that. So that's the review of Unit 5. I hope that helped. And we'll talk to everybody later.